This video goes over combinations of transformations. So we've looked at some examples of horizontal transformations, vertical transformations, and now we're putting it all together. So first thing that we're going to add in here is just some brackets, and then we're going to review all of these different pieces. So A tells us about our vertical, stretch, compression, or reflection. K tells us about our horizontal, stretch, compression, or reflection. H tells us about our horizontal shift. And C tells us about our vertical shift. So the first example that we're going to take a look at is describing how each of the following functions can be obtained from the graph of y equals f at x. So we're describing the transformations to the original y equals f at x. So the first one, we're always going to start with the stretches. So I'm going to say that there is a vertical stretch by a factor of 2. I don't have any horizontal stretches or compressions or reflections. So then I'm going to list my vertical shift up 3. And finally, I have a horizontal shift right 1. So I've dealt with my 2 in front. That was my vertical stretch. I don't have any horizontal stretch. I do have a vertical shift, and finally a horizontal shift. Let's look at the second example. So here I've got 3 things to consider. I've got a negative sign in front, I have a 3 in front of the x, and I have a -5 on the end. So I'm always going to start with my stretches, compressions, or reflections. So I can see that I have a vertical reflection, which is also a reflection in the x-axis. Then I'm going to look at my horizontal direction. So I can see that I have a horizontal compression by a factor of 1/3. Finally, my -5 at the end, I have a vertical shift down 5. So I'm looking at each of those numbers and I'm figuring out what transformation they apply to the original f at x. So let's look at a little bit more visual example. So on the right-hand side in blue, I have the graph of f at x. What I want to do is sketch the graph of each of these following transformed functions and state the domain and range, so of the new ones. So first thing that I want to do is, just like I did on the previous slide, I'm going to list the transformations. So let's see if I can add some color. So I have a number in front. I have a number inside the brackets. And I have a number on the end. So I'm always going to start with any stretches, compressions, or reflections. That would be a number in front of the function or in front of the x value. So my 1/3 tells me that I have a vertical compression by a factor of 1/3. I don't have any number in front of the x, so I don't have any horizontal stretches, compressions, or reflections. So the next thing that I see is that I have a vertical shift down 4. And finally, my +2 tells me that I have a horizontal shift left, remember x is always opposite, to the 2. So when I do transformations, lots of different ways to do it. I tend to like to use a mapping statement. So what that means is I'm going to draw out my table of values, listing the points on my original function. So I've got -4, 1, -2, -2, and then 3, 3. So my mapping statement describes what I'm going to do to each of those coordinates to get my new set of points in the transformed function. So anything that I do to x, I'm going to describe here. So a horizontal shift left 2, that is my only x transformation. So I know that I'm going to take my original x coordinates and I'm going to subtract by 2. In the y part, I'm going to put all the transformations that I'm doing to y. So the first thing that I have is 1/3. I've got a vertical compression by 1/3. I'm multiplying all of my y values by 1/3. And then I have a vertical shift down 4. Then I'm going to take away 4. I like the mapping statement because it helps me to make sure I get all my points in the right order. Once I have that mapping statement, I'm going to create a new table of values to transform these points. So my x ones are pretty straightforward. I'm going to take away 2 from each value. So my new x points are -6, -4, and 1. Y points are a little bit trickier. I've got 1/3, take away 4, -2/3, take away 4, and then 1, take away 4. So this one's easy. I can do that one, -3. The other two, I'm going to have to do some work with fractions, and I'm going to have to change to a common denominator. So let's do that now. I'm just going to change my 4s to a common denominator of 3. So I've got 1/3 -12/3, and then -2/3 -12/3. So my first y coordinate would be -11/3. My second one is going to be -14/3. So now I'm going to plot those points on the graph, and I'll do that, I don't know, let's do that in purple. I'm going to plot these points in purple. That purple looks almost black, so let's use the lighter one. Well, that's better. Okay. So my first point is -6 and -11/3. I know that's going to be just a little bit less than -4. So I've got -6, and I'm going to go almost down to -4, so about here. Then my next point is -4 and -14/3. So I know, let's see, 14 divided by 3 would be 4 point something. But it's not. Okay, so 4 point something here, put right about here. And then my last point is 1 and -3. So I'm going to connect those dots. And I've got a similar shape, but it's a little bit flatter because it's been vertically compressed. Okay, my y values are 1/3 closer together. It's been shifted down and shifted to the left. Last thing that we have to state is our domain and range. So for my purple one, I'll just write it over here. So my domain is going to go from my smallest x value, which is now -6, to my largest x value, which is 1. It includes both of those, so I'm going to use square brackets. And my range, I've got -14/3, my smallest y value, to -3, which is my largest y value. Includes both those values, so I use the square brackets. Let's try another example here. So the first thing that I'm going to do is identify my transformation. So I have a sign in front of F, and then here I've got a sign and a number in front of the X. So I've got 3 transformations that I have to identify. And we'll separate this one into 2 here. So my first one is I'm looking for any stretches, compressions, or reflections. So I do have a vertical reflection, which is in the x-axis. I also have a horizontal reflection. And finally, I have a horizontal compression by a factor of 1/2. Remember, anything that you're doing to that x is always the opposite. So let's take a look at our original table of values. So same points as before, -4, -2, 3, 1, -2, 3, and then I'm going to create my mapping statement. So you don't have to use the mapping statement. I find it helps me to organize my thoughts. The only thing, I'm doing two things in my x direction this time. So the first thing that I'm doing is I'm reflecting, so I'm multiplying everything by -1. And I'm also multiplying by my 1/k, or half. So those are the two things that I'm doing to x. The only thing that I'm doing to y is reflecting those points. So I'm just going to multiply all my y coordinates by -1. That's going to give me a new table of values. So my x's, I'm going to end up with 2, 1, and -3/2. My new y values, I'm going to have exactly the same numbers, except the signs are going to be reversed. So let's plot this in. Let's use a light blue here. So I've got my first point is 2, -1. Then I've got 1, 2. Then I've got -1.5 and -3. And I'm going to connect those dots together. So here and here. So it's been flipped both directions, horizontally and vertically. And my x points, or x coordinates, are half as close as, or twice as close as they were before. So let's state our domain and range for that light blue function. So domain is always our smallest x value to our largest x value. In this case, we're going from -3/2 to +2. Our range is going from -3 to 2, our smallest y value to our largest y value. Okay, one more example. Here we're given a parent graph, f at x equals root x, and we're going to sketch the graph of each of the following, state the domain and range, and the base equation with all transformations included. So a little bit different scenario. We have a parent function, okay, but we're still going to do the same things to start off with. So first thing is to identify all the pieces that are transformed. Here we've got 3 things in our first example. So the 3 tells us that we have a vertical stretch by 3. The blue negative sign tells us that we have a horizontal reflection. And the green half tells us that we have a horizontal stretch by 1/k, which is by 2. So then I'm going to graph my parent graph in black. I know I'm looking at the square root function. So I've got 0, 0, 1, 1, 4, 2, and 9, 3. All I really need to do in this one when I'm doing my transformations is I can still use my mapping statement, but I can also think about each point and reflect them. So I know that I am going to take my x's, I'm going to change signs, and I'm going to multiply them by 2. My y's, I'm just going to multiply them by 3. And this is my mapping statement that I'm going to use. So in my original function, I had 0, 0. I had 1, 1. And then I had 4, 2. In order to switch to my new y values, I'm going to apply my mapping statement. So my x's, I'm multiplying them all by -2. My y values, I'm multiplying them all by 3. That's going to give me my new set of points, so I'll use purple for this first one. So I still have 0, 0. Now I've got -2, 3, and -8, 6, which then I'm going to follow the general shape of my square root function, which looks like that. My domain is now going to be starting at -infinity all the way up to and including 0. My range is still everything above 0. We can also state an equation since we know the parent function. So my equation here, I would have a vertical stretch by 3, so that is outside. And then underneath the square root, I would have -1/2 x. And that's going to make sure that I get those transformations. So if I were to plug in my points to this new equation, I would get this table of values here. Let's try our second example to finish up. We've got a lot more pieces here. So I'm going to circle all my parts. I see yellow here. Okay. Now something that is really important to notice is that inside my function brackets, so right here, that expression is not factored. In order to be able to determine the transformations, you do need to factor that expression. So I'm going to take 1/2 out of both of those terms, which is going to leave me with 1/2 x minus 4 and then plus 3. So now identifying my transformations, I'm going to start with my stretches, compressions, and reflections. I have a vertical reflection. I have a horizontal stretch by 2. I have a vertical shift up 3. And last but not least, I have a horizontal shift right 4. Remember, everything that happens to x is the opposite. So let's start with our same table of values. And then I'm going to create my mapping statement. So my old x and y, on my x coordinate, I have a horizontal stretch by 2. And I have a horizontal shift to the right by 4. Then I'm going to apply my vertical transformations to the y. So I've got a vertical reflection. And I'm shifting up by 3. This is going to give me my new table of values. So my x coordinates, I'm multiplying by 2 and adding 4. So I'm going to get 4. 2 times 1 is 2, plus 4 is 6, 8, and 12. And then on the right-hand side, I'm multiplying by -1 and adding 3. So I get 3, 2, minus 2 plus 3 is 1. And now I can plot those ones. I'll use the same light blue color I did on the last side right here. So I now have 4, 3, 6, 2, and 12, 1, which I can't fit on, let's see, 10, 11, 12, and 1. So here my graph is going kind of like this, okay, which makes sense because I had a vertical reflection, so it's flipped. The last thing that I have to do is state my domain and range and do the equation. So my domain is going to be anything from x equals 4 all the way to positive infinity. So x equals 4 inclusive all the way to positive infinity. My range is a little bit trickier. I'm going to go anything from, let's see, I would have negative infinity all the way to positive 3. So looking at it from a little bit different perspective. And then I'm going to write my equation, including those transformations. So the only vertical things that I have are a reflection, and I also have a shift up 3. To the x, I've got a horizontal stretch by 2, so I'm going to have a half in the equation. And I also have a horizontal shift right 4. So I'm going to put minus 4 in here. I'm just going to rewrite that so it's a little bit bigger. Y equals minus root 1/2 x minus 4 plus 3. Those are some examples of applying all types of transformations in one particular equation.